In this lecture, let's discuss the minimal variance control for non-minimum phase systems. The dynamical equation is described by this equation. First, let's convert the polynomial, the reciprocal polynomials, A star, B star, C star, into the polynomials A, B, and C. To complete the conversion, we can use this relationship. For the A star, it will be, so assume the polynomial AK is order of K. So therefore the A star K will be Z negative K AK. In this case, the polynomials of A, B, and C, they are all of order N. And therefore, so A star will be, so Q negative N A, so B star will be Q negative N B, the C star will be Q power of negative N, then C. Then we can multiply, so Qn on both sides of the equation. This results in this dynamic equation, AY equals B ut minus K plus lambda C E. Now let's assume the polynomial BZ can be factored as B1 times B2. Let's go back to the earlier slides to know the definition of B. So the B is defined as BP times AD. We know the polynomial AD is always stable. That means all roots of the polynomial AD are within the unit circle. For BP, it may have some roots outside the unit circle. Then we assume the polynomial B1 is of degree N1. All its roots are inside the unit circle. And the polynomial B2 is of degree N2. All its roots are outside the unit circle. Then using the minimal variance control strategy, we know that UT is negative, so G star over B star F star times YT. Again, so let's convert the reciprocal polynomial to G star, B star, F star into G, B, and F. Again, we'll use this relationship. So the G star is a polynomial. So G is a polynomial of order N-1. So therefore we have, so Q negative N-1. Polynomial B is of order N. So we have the Q. So here will be the times G. So the B star will be Q negative N times B. Then F, the polynomial F is of order K minus 1. So therefore we have Q, so negative K minus 1 times F. Then therefore, so the power of Q will be the negative, so N minus 1 plus N plus, so K minus 1. So here we have negative, so minus N plus 1. We have plus N minus 1. So therefore, the power of Q is K. So therefore, the UT will be negative Q power of K. So G over B times F y T. Now let's introduce this control law into the dynamic equation. So let's change this. So the UT is so negative QK, so G over B F y T. Then let's multiply the Q negative K on both sides of the equation. Then this is 1. Okay. Then if we use the backshift operator, so the Q power of negative K will be UT minus K. Okay. Therefore, we know that the UT minus K, so will be so the negative, so B times G over B times F. Okay. So first, we cannot cancel the polynomial B because the B is not a stable polynomial. Okay, so B is not a stable polynomial. Then, so let's multiply so BF on both sides of the equation. So the left-hand side will have the AB, so ABFY, so minus BG. So here is YT as well. Then times, so BCFE. So BCFE. So therefore we have something like this. So it should be the B, so BAF plus G YT equals lambda BCFET. Okay. So we know this is F star and G star, so they satisfy this identity. Again, let's convert the reciprocal polynomial, so A star, C star, F star, and G star into C, A, F, and G. Again, we will use this relationship. So you know C star, so C star is of order n. So therefore it will be so Q negative n times C. Then A star, it is of order n, again it will be Q negative n A. So F star is a polynomial of order k minus 1, so therefore will be so Q, so negative k minus 1 F, then plus Q negative k. Then G star, so G is a polynomial of order n minus 1, so therefore it would be Q negative n minus 1 times G. Okay, then let's multiply, so Qn on both sides of the equation. So this is gone, so this is 1, this is 1. So here, so we have, so this negative n is gone, so we have the Q plus 1, so therefore, so this one will be, so Q negative k minus 1. Okay, then next, so let's multiply, so k, so Q k minus 1 on both sides of the equation. So therefore have Q k minus 1. So this is negative k minus 1. So this is gone. So this is gone. Okay. So therefore we have this equation. So the Q power of k minus 1c is AF plus G. Okay. Then we introduce the AF plus G. Okay. We replace AF plus G with the k power Q power k minus 1 C. Then we have the closed loop transfer function. The closed loop transfer function will be the yz over ez. So this is the output, this is the input, will be the lambda. So bcf over, so zk minus 1, so bz over cz. We know the poles of the transfer function define the modes of the system. Therefore, so there are k minus 1 modes with the poles at the origin. So they are within the unit circle. So we have n modes with the poles at the roots of B. We have n modes with poles at the roots of C. The factor BC cancels in the transfer function. So this implies that for the modes associated with BC, are either unobservable from the output Y, or the corresponding state variables are not controllable from the input E. So the input might excite all the modes associated with the solutions of the calculus polynomial. So this is the calculus polynomial. Then if you like it to be 0, this is the calculus equation. So this is not a serious problem if the modes are stable. Okay, if all the modes are stable, this is not a serious problem. But however, if some modes are unstable, it's possible to get infinitely large errors for some unstable modes. So this situation will occur. So if the polynomial b times c have roots outside or on the unit circle. So it follows from the representation theorem for stationary random process that C, we can always be chosen to have zeros inside or on the unit circle. So as far as C is concerned, so the only critical case for C, so would be if C has a 0 on the unit circle. So the polynomial B will have zeros outside the unit circle. So if the dynamics of the system is non-minimum phase. Okay. So it will cause some problems. So if the system is a non-minimum phase system, there are many ways to obtain control laws for non-minimum phase systems, which the closed loop system does not have unstable modes. The closed loop system does not contain any unstable modes. So one possibility is to proceed as follows. So let's design a suboptimal control. So we will need to solve this identity to find F and G. So if you compare with the minimum variance design, so the only difference is we put the polynomial, the B2, to know the early definition of B2. So B2 is an unstable polynomial. All its roots are outside the unit circle. So here, so we put the polynomial B2 in this identity to design the controller. Okay? So this one will be the same. It's not the same. Okay? It is similar to the identity we have earlier to design the minimum variance control. So only difference is we put the polynomial B2 here. So again, so let's convert the reciprocal polynomial. So C star, A star, F star so the B2 and G, so into C, A, F, B2, and G. Again, we'll use this relationship. So we know the C is this polynomial C is a polynomial of order n. So therefore we have so Q power of negative n times C. So A here, so A will be so A is polynomial of order n. So we have the Q, so negative n times A. So pay attention here. So the F star, so before the polynomial F is of order K minus 1. So here, so the order of F is not K minus 1 anymore, to be K plus N2 minus 1. So therefore we have, so Q, so negative K plus N2 minus 1. Then times F. Then the B2 is a polynomial of degree N2. Therefore we have Q, so negative N2 times B2. Then G, so G, it is still a polynomial of order n minus 1. So therefore, the G star will be, so Q, so negative n minus 1 times G. Then first, let's multiply, so Q power of n on both sides of the equation. So this is gone, because this is gone. Then this will be, so this will be negative n, and plus n should be 0. Then we have plus 1, so we can put it here. So it'll be the negative K negative n1 minus n2 minus 1. Then if we combine this, it will be, combine them together, it will be Q, so negative, so n2 plus K minus 1. Then next, so let's multiply, so Q, n2 plus K minus 1 on both sides of the equation. So here we have the Q and 2 plus K minus 1C. And this is gone, it will be A times F. And this is gone, we have B2 times G. If we use this identity and go through the same arguments used when deriving the minimum variance control law, then the control law, the new control law, is given as ut is be negative. So Q power of K, so G over B1 Q over F. So if you compare with the minimum variance control law, so here will be B. Okay, it will be the negative. So Q power of K, so G over BF. In the suboptimal design, so the controller is negative. So GK, so QK, so G B1 over B1F. This control law, so we give the control error. So the YT is lambda. So ET, F ET minus 1, FK minus 1, ET minus K plus 1. Because this F is an order of K plus N2 minus 1. So therefore, you continue. So until, okay, fk plus n2 minus 1, so e t minus k minus n2 plus 1. Then this control law, so this control law, it is not optimal. Okay, then it gives an error with the variance. The variance, so this part will be the variance of the minimum variance control law, then plus some lambda square, so fk squared until fk plus n2 minus 1 squared. Okay, so this coefficient, so f1 and fk minus 1 will be exactly the same with the minimum variance controller than the resulting coefficient of f. So to see this, so let me give you a very simple example. So let me show you a very simple example. Let's say the A, because this F, so this F is a quotient with C is divided by A. Okay? So let's assume, so the polynomial C will be just 1 plus, so C1, like say Q1 plus C2, so Q negative 2. Then if we divide this by, so 1 plus, so A1, so Q1 plus A2, Q2. Okay? So in the minimum variance controller, for example, like assume, so this K, okay? If I assume this F, we have like like say the K, okay, is just 1. So therefore we know this F is just 1. Okay, so be here. So if you do long division, here be 1 plus, so the A1, so Q1 plus A2, so Q of 2. The remaining part, so here will be the C1 minus A1 to the Q1, then plus, so C2 minus A2, so Q of 2. Okay, then if this minimum variance controller, so the K will be the 1. So here if we factorize the Q negative 1, then the remaining part, so C1 minus A1, so plus C2 minus A2, so the Q, so this will be G in the minimum variance control. Okay, so because here we have the B2, so that simply means we need to continue the long division. Okay, but the coefficients will be exactly the same. So with the minimum variance control, okay, we just need to have this F with a higher order. Okay, so then if the B2, okay, for example, the N2, so N2 is 1. We just need to continue. Like say the next coefficient will be, so C1 minus A1, then Q negative 1. So here we have, so C1 minus A1 will be Q negative 1 and plus A1, so C1 minus A1, and Q negative 2, and so on. Okay, so the point I would like to make is that, so even though we put the B2 star here, so it will not affect the coefficients of F. Okay, so what matters here is just the degree of F. Okay, if F has a higher degree, higher order, that means we just need to continue this with more coefficients. So in other words, so when we add the B2 here, it not affect the coefficient, whether we have the B2 here or we don't have the B2. So the coefficient of F1 until Fk minus 1 will be exactly the same. Okay, so therefore, so the variance of Y, so will be the minimum variance. So it will be this part. So minimum variance, this would be the variance if we use the minimum variance control law. Then if you use the suboptimal control law, so we have like additional variance. But this is not the optimal control, but it will give us the benefit, okay? So that the closed loop transfer function will not have unstable modes. Okay, so let's see this. Okay, so again, so let's introduce this control law into the dynamic equation, Okay, so again, we multiply Q powerful K on both sides of the equation. Then this is gone. Then the left hand side we have U T minus K. We have UT minus K. Then the UT minus K, so here will be the negative. So the G over B1 F. And here is YT. Okay. So again, so even though we know the B1 is stable, maybe let's not like say B1 is stable. So the B can be factored as B1 times B2. Okay. So maybe first let's not cancel the B1, even though the B1 is a stable polynomial. Okay, so let's multiply the B1F on both sides of the equation. Then we have something like this. We have the B1, here. Okay, then the left hand side we have the AF, then plus the B2G, this is YT. Then here we have the lambda times B1 CFE. Then based on the suboptimal control design, we know this AF plus B2G will be just the Q and 2 plus K minus 1. Okay, times C. Okay. Then we can find the closed loop transfer function. Okay, so this will be the closed loop transfer function. So Y is output. So A is the input. So it will be lambda, so B1 times C times F over Z, so power of N2 plus K minus 1, so B1 times C. Now it follows from the definition. We know the all roots of B1 are inside the unit circle. So that means, so the B1 is a stable polynomial. So all the roots are inside the unit circle. Therefore, we can cancel B1. So no problem. Okay, that stable polynomial is either uncontrollable or unobservable. Then for C, so we can assume we know, so we can choose for the C. So let's go back again to see how this C is defined. Okay, so this is C. So the C will be CD times AP because we assume that the AP so is a stable system because then all the roots of AP are within the circle. Then the CD, so for stationary process, so the CD can always be chosen to have all its roots inside or on the unit circle. So here, so if we make additional assumption that C has no roots on the unit circle, then this is C. Again, the C will be a stable polynomial. Then all the roots of C are within the circle. Then we can cancel C as well. So in other words, so almost of the closed loop system using the suboptimal strategy are stable modes. All the modes are stable modes. So if you compare the transfer function under the minimum variance control law, then we have the B, so the B is B1, B2, okay? Then you can see, so in the suboptimal design, so this B becomes Z and 2, okay? In the suboptimal design, so the B become Z and 2. So that means, so this control law, the suboptimal control law, so brings the roots of B2 to the origin. Okay? So here will be the roots of B2. There are other control strategies, so which instead of moving the roots of B2 to 0, so we can move the roots of B2 to arbitrary to arbitrary positions inside the unit circle. So this suboptimal strategy can also be used to make the closed loop system less sensitive to parameter variations.